Hey guys, and welcome back to another video. In this video, we'll be talking about special derivatives. Alright, so let's get right into it. Okay, so basically we're just going to be talking about some common derivatives of some common functions, right? So we'll start off with the trigonometric functions, the sig trig functions, and then we'll take the derivatives of the inverse trig functions, and then we'll go on to like e to the x and the natural log function, and then logs and exponentials with other bases. Okay, so let's get started. So I'm just going to write a list of the derivatives of the functions, and basically this is just like you have to like just memorize the derivatives essentially. Okay, so and that just comes with like practice problems. So we'll do some practice problems after I go through all the derivatives. All right, so let's get started. So first we have the derivative of sine x. This is equal to cosine x. Okay, and then the derivative of cosine x is negative sine x. And again, these derivatives can just follow from the definition of the derivative, right? So you can like try that on your own, or if you want, I can make a video of explaining how you get these derivatives. Okay, anyway, next we have derivative of tangent is equal to secant squared. Derivative of cosecant is negative cosecant x cotangent x. Derivative of secant is secant tangent. And then finally the derivative of cotangent is negative cosecant squared. Okay, so there are some like cool ways that you can memorize these derivatives. So sine x and cosine x, like that's just like pretty straightforward, right? Derivative of sine is cosine, derivative of cosine negative sine. Um, these functions show up a lot in our derivatives, so hopefully we'll just have these memorized just through like pure just practice. Okay, so the ones that are really like maybe tricky to memorize will be like these last four, but then these have a cool trick behind them, right? So notice how tangent x and secant x are related because the derivatives contain to the functions, and then similarly cosecant and cotangent are related. So the rule for the derivatives is that whenever you have secant and tangent, like together, you should always have two secants and one tangent. So what I mean by that is like, for example, if you have the derivative of tangent, so that's one tangent already. So then you need two more secants to make a full trio, right? So that means that the derivative must equal secant squared, because now you have two secants and one tangent. So then you're good. And then similarly, if you have the derivative of secant x, you already have one secant. So then that means you need one more secant and you also need a tangent. That way you have two secants and then one tangent in total. So therefore the derivative of this will just be secant x tangent x. Alright, so whenever you have tangent or secant, you always need two secants and one tangent, and then you have a full trio. And then for cosecant and cotangent, it's the exact same thing, except you always have to remember to put a negative out front. So you always need to have two cosecants and then one cotangent to make a full pair of three. So that's why like the derivative of cosecant, you already have one cosecant, so you need one more and then a cotangent, and then always put a negative out front. And then cotangent, you already have the cotangent, so you just need two more cosecants. So you have cosecant squared and then put the negative out front. Okay. And that actually goes for like all like the something. For example, even cosine have a negative out front. So whenever you have like something, you always have to put a negative. And this is also true when you get into the derivatives of inverse trig functions, which we will do next. Okay, so now let's differentiate the inverse trig functions. So derivative of inverse sine, 1 over the square root of 1 minus x squared. Okay, and you should hopefully notice some patterns as I'm writing these down, because the derivative of inverse cosine is like literally the exact same thing as this, except with a negative out front. right? So that's why you really only need to do the derivatives of inverse sine, inverse secant, and then inverse tangent, because then the derivatives of the co-evolve, so like cosine, cotangent, cosecant, is just a negative out front, okay? So then we have the derivative of inverse tangent is 1 over 1 plus x squared. So that means that the derivative of inverse cotangent, yup, you guessed it, is just negative 1 over 1 plus x squared. So this is like pretty nice, right? And then finally, the derivative of inverse secant is 1 over, this is probably like the hairiest one out of all them all, and it's really not even that bad, but it's 1 over absolute value x, and then the square root of x squared minus 1. So two things I have to note out or point out is that this looks very similar to the inverse sine derivative. The only difference, or the differences, is that first of all you have an absolute value of x out front, and then second of all here you have 1 minus x squared, but here you have x squared minus 1. Okay, so remember to keep note of that, the order of the subtraction. So in secant inverse it's x squared minus 1 in the square root, and in sine inverse it's 1 minus x squared. Okay, and then obviously the derivative of inverse cosecant is just negative of this. Okay, coolio. So now I'll let you take a moment and just like absorb all this information. All right, cool. So yeah, you pretty much just have to like memorize these derivatives. There's not really any other way around it. And like I showed you some of the tricks that you can use to memorize it, so you can just use those as well to help you. All right. So now that we have the trig derivatives down, let's move into exponentials and logarithms. So first of all, we'll start with the derivative of e to the x. And this one's actually super fascinating because, believe it or not, the derivative of e to the x is just itself. So just e to the x. And this is like, I think, one of the only functions that satisfies this property, if not the only function. All right. So this one's obviously like super easy to memorize. Just the derivative of e to the x is just e to the x, right? So that shouldn't be a problem. Next, we have the derivative of the natural log function, right? So this is like log base e. I'm sure you already know that. So the derivative of natural log of x is simply just 1 over x. All right, cool. So this is when we have base e, right? But if we have some like other arbitrary base, then how do we take the derivative? So let me show you. So if we have the derivative of a to the x, where like a is any real base, right? So this is really just the special case when a is equal to e, and you'll see how that simplifies out in a moment. But if we just generalize this to any a, then the derivative of this is just a to the x natural log of a. So then notice that if we set a equal to e, then this results in e to the x times the natural log of e. Well, what is the natural log of e? That's just 1. So that's why the derivative of e to the x is just itself. Right. Right. Cool. And then we did it for exponentials, so we also have to do it for logs. So then what if we have the derivative of log base a of some x, where again a is just some arbitrary real number. So this is just equal to 1 over x times the natural log of a. So then notice again that if we have a is equal to e, then this just becomes the derivative of the natural log of x. And so you get 1 over x times the natural log of a, which in this case is e. Again, that's just 1, so you get 1 over x. Hence, the derivative of natural log is 1 over x. All right, cool. But yeah, these 4 derivatives plus the 12 trig derivatives on the previous board, that's all the special derivatives, or like the major special derivatives that you need to know for calculus. All right, coolio. So now let's do some practice. Okay. So example 1. Calculate the derivative. Alright, so first up we have f of x equals e to the x times cosine x. Alright, so these we have like 4 practice problems. These are basically going to encompass all the derivative rules we've learned so far. So like we're talking about like power rule, product rule, quotient rule, all that, chain rule, and then plus all the special derivatives that we learned in this video. We're going to use all that knowledge combined together, and then we're going to evaluate these derivatives. Okay, so for example, for this one, we have e to the x times cosine x, right? So we have a product of two functions. So therefore, in order to find f prime of x, we should use the product rule, right? So again, what does the product rule say? It says that you differentiate each function one at a time. So we can differentiate e to the x first. So what's the derivative of e to the x? It's just itself, right? So just e to the x, and then you keep the second function. So you keep cosine x plus, now you keep e to the x. So this is sometimes very tricky because the derivative of e to the x is just e to the x. So you don't really know when you're differentiating it and when you're not. But I'm going to tell you that we know that we're differentiating e to the x down here. So this e to the x is the derivative of this one, and then we're keeping cosine x plus. So now this is just that we're bringing the e to the x down. So now we're going to differentiate cosine. Okay. So what's the derivative of cosine? Well, if you remember from the derivatives that we just went over, the derivative of cosine is simply just negative sine. Okay, and now we're done. We don't have to use chain rule or anything because there's no nested functions, no composition. So we just simplify this. So notice, first of all, we can factor out the e to the x. And then inside we have cosine x minus sine x. Alright, so this is f prime of x. Alright, cool. Alright, let's try another one. So now we have a slightly more trickier one. We're going to let f of x be log base 2 of the inverse tangent of x squared. Okay, and we want to find f prime. So note that this is really just like a composition of like 3 functions, right? So first, our most inner function is x squared, and then our second inner function is tangent inverse tangent, and then our outside function is log base 2, right? So clearly we have to use the chain rule. So what does the chain rule say? It says that you have to take the derivative of the outside function first, leaving everything inside as it is, and then once you do that, then you take the derivative of the inside function, and then the next inside function, and then so on. So basically, first what we have to do is we have to take the derivative of log base 2. So from the derivative of a logarithm, we know that the derivative of log base a of x, where a is just some arbitrary number, this is equal to 1 over x times the natural log of a. Okay, so therefore applying this for when a is equal to 2, right, because log base 2, we have that the derivative of log base 2 of x is just equal to 1 over x times the natural log of 2. Okay, so we can put that right here. So here we have x as our input. So x is really just denoting the input of the log base 2 function. So in our case, our input of log base 2 is inverse tangent of x squared. So instead of x, I'm going to put this expression, right? So we have the derivative of log base 2 of inverse tangent of x squared is 1 over inverse tangent of x squared times the natural log of 2, right? And now I'm going to multiply by the derivative of inverse tangent of x squared, okay? Because I have to take the derivative of this now and then multiply. So now we have to recall what is the derivative of inverse tangent. Well, we just went over this. The derivative of inverse tangent of x is simply just 1 over 1 plus x squared. Okay, but then again, here x is just the input of inverse tangent. So our input of inverse tangent here is x squared, not x. So instead of x to the first power squared, we're going to have x squared squared, which is x to the fourth. So then the derivative of inverse tangent of x squared, according to our rule, is just 1 plus x squared squared. And then again, one last time, we have to multiply by the derivative of the input function, so x squared. And so the derivative of x squared by the power rule is just 2x, right? Because you simply, so the derivative of x squared is just n x to the n minus 1. So in this case, n is 2, x to the n minus 1. So 2 minus 1 power, which is just 2x to the first, so just 2x. Okay? Good. So now that we have completed our chain rule sequence, we can just simplify. We can combine all our terms together. So we get f prime of x equals. So first we have, let's see. So in the denominator, we have inverse tangent of x squared times the natural log of 2 times 1 plus x to the fourth, right? And then on the top, we have 2x. So I believe this is as simplified as this expression can get. So I think this is our final answer, right? Cool. All right, now let's do another one. Okay. So just like notice how we're like basically using all of our derivative rules just to evaluate one derivative, right? So these are definitely very like heavy rule, like formula wise. Like once you get a hang of it, it honestly isn't that bad. All right. So next we have g of x equals the natural log of e to the x sine squared x all over x cubed. Okay. So once again, we have a composition of two functions, right? So our first outside function is the natural log function, and then our inside function is this whole expression. So therefore, we have to use the chain rule. So g prime of x equals. So first, we just treat everything inside natural log as one single variable. So we'll just like set this whole thing equal to u, let's just say. So then we just have to differentiate the natural log of u. Well, we know that's just 1 over u, right? Because the derivative of natural log is just 1 over x. So we just have 1 over this whole expression. So we're essentially just taking the reciprocal of this. So we have x cubed over e to the x times sine squared x, right? Because if we take 1 over a fraction, that's just taking the reciprocal of the fraction. So we have that, but then don't forget, we have to use the chain rule, so therefore we have to multiply by the derivative of u, which is this whole expression. So now our task is differentiating this expression. Well, this is a combination of multiple rules, right? So first of all, in the numerator, we have the product of two functions. We have e to the x times sine squared of x. So that requires product rule. And then we have that whole thing over x cubed. So we have a quotient of two functions, and so that requires quotient rule. And then also notice that we have x cubed and then sine squared. So those both require power rules separately. So this is like a whole combination of derivative rules. But don't worry, we'll take it one step at a time and we'll solve this derivative. Okay, so first let's just, the whole thing is really just a quotient, right? So I'm going to start by using the quotient rule. So the quotient rule, remember that says low d high minus high d low all over the square root of what's below. So I'm going to keep my low function. So I have low d high, so differentiating this function. So now we have to use the product rule in order to differentiate e to the x sine squared x. So product rule that says you keep the first function, so we keep e to the x, and then differentiate sine squared. So now again you have to use the chain. So like it's like a whole combination of rules, but don't get overwhelmed, right? If you just do it slowly, you can definitely get the right answer. So this is what we did so far, right? So we kept e to the x, and now you want to differentiate sine squared. So what's the derivative of sine squared? Well, this can be rewritten as sine of x squared, right? So we can treat sine of x as a variable for now, and then we just really have u to the power of 2, right? We have some variable squared, so you have to use power rule, right? So the derivative of x squared is just 2x. So in this case, it's 2 sine x. But then now you have to multiply by the derivative of the inside function, which is sine x. So the derivative of sine x is cosine x. So the derivative of sine squared x is 2 sine x cosine x. So I'm going to multiply that here. Okay? And then plus. So now we differentiate e to the x. That is just e to the x. Okay, the derivative of e to the x is just e to the x. And then we're going to bring down my sine squared. I'm going to keep that the same. So that was low d high. Okay, so that's the first part of the quotient rule. So then now we have minus high d low. So now we're going to keep the high function. So we're keeping e to the x sine squared x. And then I'm differentiating x cubed. This is just a simple application of the power rule. So we have x cubed, differentiating this. So this is just equal to nx to the n minus 1. So n in our case is equal to 3. So we have 3x to the 3 minus 1 power, which is just 2. So the derivative of x cubed is just 3x squared. Alright, so now we have low d high minus high d low. High d low. All over the square of what's below. So now we just have to divide all of this by x cubed squared, which is just x to the 6th power, right? We divide everything by x cubed squared. So this can definitely look a little overwhelming, but don't worry, it like all cancels out very nicely in the end. Okay. So to begin, I will just split this fraction up into two separate pieces. So I'll just have this first thing all over x to the 6th minus this whole thing over x to the 6th. And then I can also factor out, so notice I can factor out an e to the x from both of these terms, and I can factor out a sine x. So I will do just that. So I have x cubed e to the x sine x times. So here I'm left with a 2 cosine x, and here I'm just left with a sine, all over x to the power of 6, right? Minus. Here, it's already factored out for the most part, so I just have 3x squared e to the x sine squared x, all over x to the power of 6. Okay. Actually, what I'm going to do is I'm going to actually combine these two fractions together, because I believe that will make it slightly easier. So instead, what I'm going to do is I'm just going to combine these two fractions together. So notice I can still actually factor out an e to the x, a sine x, and an x squared. So all I really have to do now is I just have to redistribute back an x. So I have x squared e to the x sine x is a common factor for all three of these terms. Okay. So then over here, what am I left with? Well, I have a 2x cosine x plus x sine x, right? And then minus 3 sine x, all over x to the power of 6. Okay? So then x squared cancels with x to the 6th, and this becomes an x to the 4th. Okay? So then this becomes e to the x sine x times 2x cosine x plus x sine x minus 3 sine x all over x to the fourth. Okay, well then just remember that this whole expression is only the derivative of this inside expression. So, because originally we had done chain rule, right? We took the derivative of natural log first, and we got this. And then we were trying to multiply that by the derivative of this. But now we have found the derivative of the inside function, it's just this. So we have to take x cubed over e to the x times sine squared x and multiply it by this whole expression. So then now notice how everything just seems to cancel out. So that's what I'm going to do now. So I'm just going to multiply this whole thing by this fraction. Okay, so I will just erase all this. I'm just going to write this whole expression right here and then just like watch everything for the most part just cancel out. Alright, so I'm going to get rid of all this. This is just like some side work. And so now notice, so we have g prime of x equals, alright, so e to the x cancel with e to the x, and then sine squared cancel with this sine, and we're just left with a sine x in the bottom over here. And then we have x cubed cancel with x to the fourth and just leaves an x. So, ladies and gentlemen, we have what we're left with is, so in the numerator, we're just left with this. So we're just left with 2x cosine x minus, or sorry, plus x sine x minus 3 sine x, right? So that's the whole numerator. And then in the denominator, we just left with an x sine x. All right. So now we can actually simplify this even further still by breaking this up into 3 separate fractions, right? So first, we have 2x cosine x over x sine x. So what is that? So x cancels with this x, so we're just left with a 2, and then cosine x over sine x, that's just equal to cotangent x. So we have a 2 cotangent x. Okay, and then now over here we have an x sine x over x sine x, so that's just plus 1. And then we have minus 3 sine x over x, or yeah, minus 3 sine x over x sine x. So sine x cancels, so we're just left with a negative 3 over x. So this is the final derivative. Okay. Nice. All right, so now we just have one more, and this last one is arguably the most difficult, but don't worry, we will get through it. Because I'm sure you've already realized that the derivative part isn't the hardest, but rather the simplifying is the harder part. All right, so then next, lastly, we have h of x is equal to 5 to the power of the square root of e to the 3x plus 2 to the x squared. Okay, so don't panic. This is very manageable. All right, so first notice that we have 5 to some function u, right? So if you want to differentiate this, what is this equal to? It's just equal to 5 to the u natural log of u, right? So we have to use the chain rule for this, right? So we're going to treat this whole square root expression as some u, right? And so then we're just going to differentiate this how we usually would. So h prime of x is just equal to, so we have 5 to the u, so we're basically just carrying this down, times the natural log of u. So natural log of this whole thing. All right, cool. So then now we have to use chain rule. So what that means is you have to multiply this whole thing by the derivative of the square root. All right. So let's just differentiate this square root separately, and then we'll bring it back in the end. So we have the square root of e to the 3x plus 2 to the x squared. Well, this is just the same thing as the 1/2 power, right? So remember I said that converting between square roots and 1/2 powers is going to be a super common practice. And the reason for that is because now we have written this as some function to, or some like variable to an exponent. So now we can just apply the power rule. So that's very nice. So power rule just says that we bring this out front and we subtract 1. So the derivative of this is just equal to 1/2 e to the 3x plus 2x squared to the negative 1/2. Or in other words, it's just 1 over 2 times the square root of this expression. All right, but we're not done, because now we have to use the chain rule still again, because we have to now multiply by the derivative of the expression inside the square root, so namely e to the 3x plus 2 to the x squared. So the derivative of e to the 3x, that is just equal to e to the 3x, and then again we have to use chain rule, so because we have to multiply with the derivative of 3x, but the derivative of 3x is simply just 3. Okay, so the derivative of e to the 3x is just 3e to the 3x. And now and then we add plus the derivative of 2 to the x squared power. So 2 to the x squared. Again, this is just if we have 2 to some variable u, how do we differentiate this? Well, this is just equal to 2 to the u natural log of 2. Alright. Oh, I am extremely sorry. Over here, I wrote natural log of this expression. It's actually supposed to be natural log of 5. It's always natural log of the base. So this should be times natural log of 5. I'm extremely sorry. That's completely my fault. Okay. But anyway, moving on. So now we have the derivative of 2 to the u. That's just 2 to the u times natural log of 2. So applying that to 2 to the x squared, this derivative of this is just equal to 2 to the x squared natural log 2. But again, guess what we have to use? That's right, we have to use the chain rule. And that's because x squared is its own separate function. So we have to multiply by the derivative of x squared. So we could just use a simple application of the power rule for that. So then we get the derivative of x squared is 2x, so we multiply that. All right, so now we are finally done, right? So this is the whole derivative of the square root expression. So now we have to take this whole thing and multiply it back to this expression. And then we have to see if anything cancels. All right, so let's do that right now. So we take this whole thing and we're multiplying it by this. So we have times 3 to the 3x, 3e to 3x plus 2 to the x squared natural log of 2 times 2x all over 2 square root of e to the 3x plus 2 to the x squared. Okay, so I don't think anything will cancel that much. So this is our final answer. Alright, so hopefully this video helped you get better at like just taking derivatives in general, and now you also learned the derivatives of the special like trig functions and like natural log e to the x, right? So if you found this video helpful, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.